Okay, so it's wonderful to be here. So we heard in the last talks about a number of biases, behavioral and cognitive biases, in the talks of Mike, of Luminita, of Tomasz. Tomasz in particular mentioned a number of biases like the decoy effect, the gambler's fallacy, the hot hand fallacy, and these examples that show that people have the nerve not to follow the desirable axioms. And I will focus on these kind of biases in this lecture. Now, if you look up these biases, you see that a very large number of cognitive biases have been reported in the literature. I don't think this picture is very scientific, but it tries at least to categorize these biases in different categories. I will not discuss all of them, but I will touch upon a few of them, like indeed the gambler's fallacy, the recency illusion, the hot hand fallacy. And if you look cognitive biases on the web, you find even less scientific illustrations like this one that says 50 cognitive biases to be aware of so you can be the very best version of you. So I thought I would show you this, so if you don't like the lecture, at least you'll appreciate the therapeutic value of it. So, and here again, they mention the gambler's fallacy, that Alice has lost 9 coin tosses in a row, so she's sure to win the next one. And that's exactly the kind of scenario that the entire lecture will be set up in. It's a scenario in which you have discrete periods or trials, and on each trial you will receive a signal or a piece of information. Typically that signal will be noisy, and on the basis of this signal, you as the agent, the decision maker, will have to produce some action on each period according to some prescription, and I'll discuss different examples. Now that's exactly what you do when you play the roulette. You have these random signals, red or black, and you have to bet on the next turn of the wheel. And gambler's fallacy is sometimes referred to as the Monte Carlo fallacy, because in 1913, about when this picture of the Monte Carlo casino was taken, the black appeared 27 times in a row. And after the 11th time, everybody started to bet on the red, because they were convinced that the red would show up. And the casino made an absolute fortune that night. On the basis of people's gambler's fallacy. Now, a very elementary version of this gambler's fallacy, if you just look at 2 consecutive signals, one can think of it as an alternation bias. So if you see a 0 or black, you think that it's more likely that after there will be a 1, the other symbol. Now, the opposite bias, the hot hand fallacy, is kind of the opposite. I think it was first pointed out by Tversky and colleagues in the context of basketball, and the idea was when a player is playing, if he's scoring, he has a hot hand, and so he will continue to score. Now, this has been controversial. In fact, in the last 5 or 10 years, there are a couple of statisticians, Sanjuro and Miller, that showed that, in fact, most likely, it's not a fallacy, and basketball players do have a hot hand. Based on finite size effects, they reanalyzed the data. But anyways, this fallacy shows up in other contexts. And an elementary version of it is a repetition bias. So if you see a 1, you think that it will be followed by another 1, and that you think that this is more probable than a 1 being following a 0. Okay? So another way to think about this is some kind of recency effect. So recent symbols that you have seen have more weight, and so you will expect them more. You can also think of it as an overreaction or as some kind of extrapolative belief. Okay? So just as a parenthesis, it's amusing to note that Laplace was the first who noted both of these fallacies. So he noted it in the context of childbirth for the gambler's fallacy. In the context of lotteries, he noted that people would play again the numbers that gave them a win. And in the context of childbirth, he went to He visited various departments in France, departments meaning regions, not university departments, and he did a tabulation of births and deaths and marriages, and from that he did the first Bayesian estimation of the posterior probability of having a girl versus a boy, and based on his data, he found that girls were a bit less likely to be born than boys. And it's in doing this that he noticed that parents, when they have a boy, they typically expect to have a girl afterwards. And that was the first example of gambler's fallacy. Now, I cannot resist showing this because I find it so amusing that this he did when he was not so old, but later on, in 1812, he wrote all his ideas on probability in a book that he called Analytic Theory of Probabilities. And the book mentions all his decorations. Chancelier du Sénat conservateur, grand officier de la Légion d'honneur, membre de l'Institut impérial, and all his honorary degrees. So, and he was honorary fellow of Société Royale de Londres, de Göttingen, Académie des Sciences, de Russie, du Danemark, de Suède, de Prusse, de Hollande, d'Italie, etc. And this was the first edition. It went through 3 editions. That was the 3rd edition. And the most amusing is that he went from being Count to being Marquis. And that was because he was the teacher of Napoleon in school, in École Militaire. And he remained close to Napoleon most of his life, not at the end, but most of his life. And he dedicated this book to Napoleon. And that made him this posh Marquis. So if you want to be successful, you should be nice to your local dictator, and you should be a great mathematician. So what I'll try to defend is that these, the kind of biases I will discuss can be interpreted as some kind of optimality, but not a free optimality, a constrained optimality, an optimality under some cognitive limitations. Now, why is this reasonable to assume? And I will develop this kind of picture in the second lecture. Well, simply because any action that you produce is not based directly on a physical stimulus, but is based on your internal representation, your neural representation of this stimulus. And this neural representation, again, as I'll explain in more detail in the second lecture, is subject to a lot of imperfection, and in particular is noisy. So you can think of this representation as some average response to the stimulus plus some fluctuating, some random variable. Again, I will come back to this. But as a result of this, imagine that you're in period 6 and you have to produce some action in response to this signal. You will want to use the information that you had from past signals, but you don't have any more direct access to them. They've already disappeared. They're in the past. What you have access to is your mental representation of these signals. So I will try to build on this picture. So what's the outline of the talk? I will start by discussing a very simple kind of heuristic model of costly Bayesian inference. I will then briefly try to connect it to some existing models both in economics and neuroscience. And then I will spend the second half of the lecture on a more sophisticated model or more systematic model of belief updating and forecasting, which will kind of correct a number of aspects of this simple model which are not satisfactory. But before, I want to motivate this with a few more examples of biases. So imagine that you're in this situation. I show you a sequence of binary symbols. The one is me as the experimenter, as the designer of the experiment. I draw ones with probability p. I draw zeros with probability 1 minus p. And I ask you, after each time you observe a signal, to produce what you think is the probability underlying this process. Okay? So after each trial, you have to tell me what the underlying probability is. Well, if you're a rational player, which you all are, what you would do is you would simply calculate a running average. You calculate the empirical average. So you count the number of 1 that occur. You divide by the total number of symbols. And this will converge this number to the true probability of your process. Okay? Now, more systematically, more precisely, what you would do is to update some Bayesian belief, some posterior belief on the underlying probability by multiplying your estimate every time you see a 1, or 1 minus your estimate every time you see a 0. And so you will get a beta distribution for your updated belief that after a long time will converge to a delta function around the true probability of the process, that generated the process. Okay? Now, people don't do this at all. And with apologies to Ariel, I'm going to show an experiment with 1,000 trials. So this is an experiment that was part of a set of experiments by Ward Edwards in the 60s, which are quite beautiful. This was done before computers, so he did it with cardboard and papers. You had to unstick pieces of papers to see what was the symbol under and things like this. And here the subjects are doing 1,000 trials of exactly the problem I mentioned, and they have to predict what the next symbol will be. Okay? What is plotted here is the average over 40 trials. So this point is the average over the first 40 trials. These points are the average over the second 40 trials, and so on. In dashed, what you see is the actual average of the process. Okay, so in this specific panel that I'm showing, the true probability was 0.5, and in the first 40 trials there was slightly more ones than zeros, so the probability, the empirical average was above 0.5. And in the solid line, the solid line is the average over 40 trials successively of the prediction of the player. Okay? And so what you can see is two things. One is that the predictions continue to fluctuate, okay, even after 1,000 trials. Now you'll tell me this is indifferent, so you can fluctuate, it doesn't matter what you predict. But I'm just showing you this for 0.5. It looks very similar for 0.55, 0.6. So I just picked this one. I should maybe have picked another one. The other thing that you see is that the belief is correlated with what happens in the history. Okay? Now, a more recent experiment by Friedman and Nave does a very similar thing. They show two symbols, one of two symbols to people, a square or a circle, square or a disk, and they ask people to click square when they see a square and to click disk when they see a disk. Okay? And then they look at the error rate as a function of the length of a streak. So 2 is like you have 2 squares and then you have to click after the second square. Okay, Okay, and so here what you see is that the error rate for continuation goes down and the error rate for violation goes up. So if you've seen 4 squares, you're less likely to make an error on the 5th square. But if you have a violation, if you have a streak of 4 circles, then you're very likely to make an error on the next symbol, if it's a square. Now you could say, well, of course that's just a motor thing. People are just clicking, and you know, they just get accustomed to clicking on the square, and that's why they will have this error. That may be, but note that people were explicitly told that there's a fixed probability. Okay, so they're told explicitly and they're trained. So it's not like things are hidden from them. But also you can do another test to rule out this motor issue. You can ask them to say what's the probability with which the next symbol will be a square or a circle. Actually, this experiment uses slightly different stimulus, but conceptually it's the same thing. Different visual stimulus, but conceptually it's the same thing. And what you see is that the probability, you think that the probability grows as you see more squares. Okay, so the more squares you see, the more you think another square will be probable. So this is exactly like what we call hot hand fallacy. Okay, any questions? Now, this is just looking at streaks. So a set of 3 or 4 successive symbols that are the same, you can do a finer examination. So this was an experiment by Cho and colleagues. And here they look at the case where the probability is 0.5. And so they look at sequences of 5 symbols, but they write 4 because R is repetition, A is alternation. So 4 repetition means 5 ones, okay? 1 alternation and 3 repetitions means 1, 0, 0, 0, 0, okay? And then they measure the error rate for clicking on the symbol that you've seen, and you see that there's some kind of structure depending on the specific order of the history. So I'm not going to discuss that in detail. Maybe I'll mention something, but I just wanted to show you that one can do more delicate analyses on the history than just looking at street lengths. Any questions? I'm a bit worried you don't have questions, yeah.
You get a hot-hand fallacy in a situation in which you would expect a gambler's fallacy. It would confuse you.
Well, I think it... well, in some experiments you see one, in some experiments you see the other. So, for example, there have been experiments that are change the degree to which the people think that there's human agency behind the stimulus generation. And what they observe in those experiments is that people tend to show gambler's fallacy when they think that there's no human agency behind, and hot hand fallacy when they think that there's a human agency behind. So what I want to derive from this is not that that's the answer to the dilemma. What I want to derive from this is that what bias people show will be somewhat sensitive to the conditions of the experiment. And in these conditions, what you see is hot hand.
What are the subjects told about the data generating process in that case?
So in this case, they see some random walk with ticks that can go up or go down. And
they're told the increments are independent.
And they're told the increments are independent, yeah.
Is it finite? Like, does it end sometime? Because in that case...
When the subject dies.
Well, in that case, there is something that does cause the probabilities to be not at 1/2. So if you think of a finite set of draws, and we're saying from that finite set of draws, we're going to pick a streak of 3 heads.
That's right. So this is exactly the analysis of San Yurio and Miller.
Right, exactly.
But here they don't see, they're not told, okay, we've picked this from some big string. They're just seeing one thing after the other. Yeah. But you're right that if they were told that, then there would be those finite side effects.
These people would have become very, very rich in Monte Carlo.
One night,
That,
and very
one
poor
night,
another
But
night.
it's kind of confusing that everybody in the Monte Carlo casino did the opposite, in the kind of the same exact situation.
That's right. That's right. I don't have a good answer for that. So now, yeah. So okay. So this was to quantify things through error rate. I think it was Ariel. You talked about response times. You can also quantify these results via reaction times, and you again see that as a function of different orders, you have different structure of different reaction times with which people answer. You can do an even simpler experiment, which is that people are just watching what happens on the screen and doing absolutely nothing, okay? And then you measure their brain activity with EEG. I'm not going to go into the detail of what this is. It's called P300 amplitude. It's a piece of the EEG response. And we know that it's associated to surprise. So you can think of this P300 amplitude as some kind of proxy for the logarithm of 1 over the probability with which they're expecting a symbol to occur, or some monotonic function of this. And what you see here, illustrated here, is that when you look at all the data combined, you have this amount for the P300 amplitude, but when you condition the data on the previous stimulus, what was the previous stimulus, 1 or 0, then the P300 amplitude splits. Okay, you have 2 different values. I will show you a better way to draw it, and you can do this with an underlying Bernoulli probability that is different from 0.5, 0.3, or 0.7, and you have a similar structure. So here is just this data redrawn. So the gray line is this surprise as a function of the underlying probability unconditional on the past history. So of course, if it's rarer, probability is 0.3, you're more surprised than if it's less rare, okay? But now if you condition the amplitude on the previous symbol, so you measure the response to a 1 that follows a 0 versus the response to 1 that follows a 1, you see that there's a split, okay? And so you're more surprised when a 1 follows a 0 than when a 1 follows a 1. And if you condition on longer histories, you have successive splits. No question?
So this is again contrary to Gambler's fallacy.
This is hot hand fallacy. I shouldn't have mentioned Gambler's fallacy because I'm going to talk about hot hand nearly only. So I got myself in trouble by mentioning the casino.
It was a cool example.
Thank you.
What about surprise after longer streaks? That is, if you see 5 zeros in a row,
Yeah.
are you even more surprised if you see?
So I have not seen. Right, so I've not seen analyses of very long streaks of a given symbol, like in the Monte Carlo, like 27.
But you have data right there?
Well, up to 5. Right.
We can compare
But I
shorts of other
No, but
streaks, not all of that.
I thought you were asking very long, like hundreds. So this is up to 5. Okay, so here you have, these are all possible 5 symbol sequences,
Right.
and you have this structure in the reaction time, which is very similar to this inverted V structure for error rate.
Right.
Now, if you're asking me about much longer sequences, like tens or hundreds of trials, I never saw an analysis of a streak, because obviously they're very improbable and you want enough statistics. But I will show you an experiment that we conducted where we look at couple hundred trials.
But that's showing shorter, slower reaction time after 4, and then an alternation, then after only 3, and then alternation.
That's right. But again, up to 5, that's the result. More than 5, I haven't seen analyses of streaks.
One quick question. So
Yes.
You also do not receive the experiments. You cannot lie.
Well, here you're not asked for verbal report. I mean, you can.
You say that the probability of showing is something, and then you cannot just show super likely.
Oh, you as the experimenter, can you lie? You could if you wanted, but I don't think they did.
Because in economics, you cannot. But some. No, I'm asking because I don't know.
So here, I don't think there is any.
They genuinely ran.
Yeah, here I think there's no what you're talking about. But what we did, for example, in an experiment is we drew a random sequence and then we used the same one many times and for many subjects. Okay, but we drew a really random sequence. You're right that one could interleave a random sequence and in some pieces put some very unlikely sequence to see specifically how people behave to that, assuming that they don't notice that this is happening. And still one could do these things, but that's not what is done here.
Before you said that the Gambler's fallacy is associated to contexts where people think there is no human being behind the experiment that they attend with. Like, so it seems that people have kind of two different theories. Do you observe people switching from Gambler's fallacy?
You do, and in fact, I mean, none of you have. I thought one of you would notice, and disappointed none of you noticed. But in fact, in the data that I showed from Friedman and Nav at very short streak, you did have Gambler's fallacy, and then you switched to hot hand. And again, my point about this human agency and so on, that was quoting just one paper. I don't know how much confidence to assign to that paper. My point was that you can manipulate these biases to some extent by changing the conditions of the experiments, and so I'm sure that you could program an experiment such that you would see a switch. How, I don't know.
But yeah, but so like, do you think it's plausible to think that people are actually have two models in a sense of the data generating process and they are switching, I don't know, after 27
Okay, so there are two questions. One is what do I think is plausible, and one is do people switch between models? The first question I cannot answer because I have to say plausible on what basis. So the second question, there is a whole literature about trying to explain these biases in the way you're proposing, namely that people have a bank of strategy and kind of pick between these strategies according to some rule that can be more or less principled. I've never been super interested in this just because of the ad hoc nature of the bank of strategies in most of these models. And so what I'm going to try to argue is for a different approach, which is to try to leave that strategy as flexible as possible and impose a natural constraint and then see whether the optimal special case of that strategy given the constraint can be compared favorably with data. But it is indeed something that people have proposed.
All the data that you showed us, if I understand correctly, is an average.
Yes.
But it's not the case that actually you can identify different times.
So again, so this is, okay, so you can, average you mean over people or over trials?
The data, when you show something, is always an average over people.
No. You can do very detailed statistical analysis
Can
over.
what you did.
Well, in here it's average over people. That I'm not sure is an average over people. That might be just one subject. I'm not sure. But I will show you experiments where we did analysis on single subjects. And I agree with you that that's what should do. And there is difference between people. There's also difference within a person. You can identify types. There are examples where people fall in categories. I could have shown you something of that sort. I probably will not.
But looking ahead to the explanation you're going to give, does your explanation account for heterogeneity across
Yes.
people? It does, okay.
One of the explanations. Okay, so I shouldn't have encouraged you to ask questions. So so let me summarize what are the stylized facts we will want to explain. The first one is that the belief continue to fluctuate even after a long time in a situation where optimally or ideally you would not expect that beliefs should fluctuate. Second, there is some kind of recency effect where recent observations are weighed more strongly. There is some kind of overreaction or extrapolative belief or hot hand fallacy. And finally, something that I haven't mentioned, but that Ariel and Eric just mentioned, is that there is heterogeneity, so there's idiosyncratic noise among subjects and within subjects. So I showed you some psychology experiments that were done on this. There's also a literature in economics. I'm sure most of you know this literature much better than me. But Ulrike Malmondier has studied individual forecasters, and one of the ingredients in the models that she needs to explain the data is precisely recency effects. De Bond and Thaler studied the stock market and found signatures of overreaction. More recently, Bordallo and colleagues have looked at individual forecasters forecasting financial data, quantities, macroeconomic quantities, and found evidence of overreaction. So how can we explain these biases?
Sorry, one question.
Yes.
Because you mentioned the recency effect, one can also think of, I think there are also work dealing with primacy effects, or the opposite,
That's
that
right.
the information that
That's
is
right.
inferred has this primacy effect.
That's right.
Is it somehow that you can say, okay, this kind of experiments, we rather see recency effects, and in that kind of experiments, rather primacy effects?
So I don't have a good mental summary of what experiments you see which. Typically you see both, and primacy effects can be quite strong. There are ways to address primacy effect also in a normative way, but I'm not going to address it in this talk. Okay, so as a neuroscientist, one way, well, I'm not, as a physicist or whatever I am, one way of approaching this is to think of mechanistic reasons. So to go down to neurons and see how neurons may adapt to stimuli and how they convey information. I'm not going to talk about this now, but my second lecture I will discuss this a little bit. If we want to bypass a mechanistic level, we can propose heuristics that are stories of how things might be happening. And so one story that has been proposed to explain the gambler's fallacy is sometimes referred to as the law of small numbers, that says that a small sample should be illustrative of a large sample. So this sequence is judged as being more random than this one. Okay? And this is kind of a very rough example of a more general story that one could call representativeness, of which some of the work of Bordalo et al., the diagnostic expectation, is a specific, somewhat more refined formulation. Again, this is not something I'm going to discuss. And what I'm going to focus on is a normative approach, namely, can we get these effects from an optimization principle? Now, if we want to get non-rational effects from an optimization principle, something has to go wrong, okay? And the typical choices that people make is to adopt some reward function or some loss function that is distorted, is not the true one, not the correct one. Another assumption that sometimes people make is that their models are misspecified. So they're optimizing within a class of models that doesn't include the true model. And there are some examples in the context of forecasting, again, that I will not discuss. And so the point of view I would like to adopt is a different point of view, is not to assume some ad hoc thing which has gone wrong, but simply to assume that there is some cost to neural representations. Okay? But other than that, people will behave optimally, or will compute optimally. So let's start with a very simple model based on this idea. And again, I'm going to go back to this picture where I'm asking you to produce some probability. Now, even though you've been told that underlying this process there's a single probability, you might think that the process is more complicated, okay? And you might think that there are temporal correlations, so you should also look at a conditional probability or at a conditional probability over a longer history. And so what you should update is not a belief only on this probability, but a belief on a more complicated model of the world that includes other parameters, okay? Now, if you do correct belief updating, if you do correct Bayesian updating, obviously all these parameters will converge to 0, and you'll just be left with the correct solution, okay? So even if you started with a more general model than your true model, you will converge to the true model. So the idea here is to say, okay, we update a very complicated belief. That's a complicated task to do. So let us constrain this by imposing a cost on that complication, okay? But otherwise do Bayesian inference. So what I'll propose is as follows. Suppose that you have a vector Q of parameters that define a data generating process. It's specified, so it encompasses the true data generating process. And I will call the belief that you hold in your head at time t p hat of Q. Okay, so that's a distribution of these parameters, and that's what you believe at time t. If you were to do a Bayesian updating, you would calculate your posterior belief at time t plus 1 as your prior belief multiplied by the likelihood of the observation you just saw given the parameters of your model. Okay? That's what you would do if you did correct Bayesian updating. But what we'll say is that the p hat, so namely the belief you store in your head, will be different from this true belief, and will be different because it's subjected to a cost. Okay? And so what we'll propose is that instead of doing pure Bayesian inference, you'll do some kind of costly Bayesian updating, where the new belief that you'll hold in your head will minimize the sum of two terms. The first term is a distance between the belief you have in your head and the correctly updated belief. And I don't have to introduce for you this which is the Kullback-Leibler divergence that Luminita has discussed in some detail. And that's what we chose as a distance. And the second term that we want to minimize is some cost on holding this belief in your head. Okay? So we tried various types of costs, and I will show you, and there are different types that give rise to different types of results. I will just show you one example because it will be useful for me to connect it to what will come later. And the cost that I will propose here is a simple entropic cost. So I will say that the cost is just minus the entropy of my belief. Okay, so if I have a flat belief, if I'm completely agnostic, I don't have to pay any cost. And as soon as my beliefs become more precise, I have to pay some cost. So it's some precision cost that I have to pay on my belief.
What is this concept
From my,
Why?
well, I just gave you the intuition. Sorry? It's a story. Sorry?
It's the opposite story.
Okay, so if you want, we looked at the opposite story. If you want, I'll tell you when we have coffee. We looked at a number of costs. The reason, so there are two reasons why I'm showing you this cost. The three reasons. One, it's a fairly natural story. Okay. Again, because so suppose you wanted to write a cost on precision, this would be a natural measure of precision. Okay, that's the first thing. The second reason is that it will adhere to some of our data, okay, which is not a reason that convinces you, I know. And the third reason is because I will show that it gives rise to a phenomenology that a more refined model confirms, and you might find that one more satisfactory, the motivations, and that, if you want, will be a more systematic explanation of this rough model. So think of this as a story.
It's more costly to hold it than precisely.
Yes. So if you don't know anything, you don't have to remember anything, you don't know, you believe anything is possible, that's not costly. If you start having opinions, it's costly.
But it seems that, I don't know, my first reaction would be almost the opposite. You know,
That to know something with...
thinking that, you know, there is thinking that something
Okay.
with probability 1 is simpler than
Okay.
contemplating
So if
many
I
possibilities.
have to convey to you something which is very precise, I will have to describe it in much greater detail. I will have to send you a much longer message, and you'll have to store much more information. So the more precise I want to make my message, the more bits of information I have to convey to you. Okay? Whereas if my message is very rough, a short sentence will do. That's the motivation behind this. I should limit the questions from the first row, following on Ariel's example. Yeah. I will not limit it to 0, let's say 1 out of 3 or 5. Yeah.
So one might have imagined a cost function that privileges simpler models over more complex models.
Yes.
So for example, models that don't involve any serial correlation. being
That's right. So
preferred to ones that are looking back one.
that's right.
later.
That's right. So one can do that. I don't have a good way of doing it. So I don't have a way which doesn't have some ad hoc assumptions I don't like. But this is something that we should
So
discuss.
often people penalize the number of parameters.
I know. So you can do that, and I think in my second lecture I will show some variant of that in the neural context. Again, I think the number of parameters is a very bad, is not a very good penalty, because, for example, it doesn't account well for the distance between probability distributions and things like this. So I'm not sure it's the natural measure, but I agree with you that that would be something that would be good to think about, to follow. Yes.
Yes, so to clarify here, the precision comes from the fact that, or the precision cost comes from the fact that you're trying to estimate as accurately as possible, like you're trying to hold a precise estimate.
That's right.
Because of your mental efforts, right?
That's
so
right.
it's more costly.
You can think of it like
As
that.
opposed to like a precise estimate of like, I don't, like, it's kind of a random estimate, but it's very precise. So maybe that answers kind of
Sure.
the
Sure.
concerns that
Yeah.
you might have a very precise estimate that's not based on any
Well, it's conditional on the
past, so
history.
it's not costly,
Yeah.
but it comes from the
think there was.
So this is all completely disjoint from magnitude of losses or gains or just.
I will come to that, but yeah, I will come to that.
Okay, also unique or not, they always tend to be
So here the loss or gain is how wrong I am compared to a Bayesian update. Okay, it's this Kullback-Leibler divergence. I've chosen it arbitrarily. I don't know why Ariel asked me about the cost and not the Kullback-Leibler divergence, but both were arbitrary.
And just like, why do you think that communication cost is a good proxy for storing cost? Like, if I have to describe something to somebody else, like, is communication, but if I have this belief for myself.
Well, because every word I'm telling, well, this belief you get from something, right? So every bit of information, so every word I'm saying now, your hair cells in your ear are moving from the air pressure that I'm sending from my mouth. Every one of these moves elicits a spike. Every spike will cost some metabolic energy. And so the more information you're willing to recruit to make your belief more precise, the more cost you'll have to pay. I'll come back to
It's
that.
about the means and not the ends, right? Like how you got to be precise and not the fact that you got precise.
I don't know. How about this? It's just a mathematical structure. You can interpret it the way you want. Because that's what it really is.
Could I ask one more question?
Please.
Sorry to slow you down. The idea that the distance from true Bayesian updating is the cost suggests that the subject is trying to Bayesian update, but can't do it because it's too costly. But if subjects have no idea what Bayesian updating even is, why is
Okay, so
distance
I'll tell you how I would rationalize this. Suppose that you're a subject that has to do a million different tasks in your life, and you want some belief of update of beliefs that will be good for all these possible tasks. Okay, in that case, you'll want your update of belief to be as close as possible to Bayesian. You will not do the Bayesian computation or this costly optimization, but with experience, you will learn that this is how you should update your belief to be good at many tasks, the same way that by experience you learn that this is how you should hit a tennis ball without making the optimization in your. Okay, so again, this was a simple model that was supposed to be the first 15 minutes or so of the talk to motivate a more richer model. So maybe don't slow me down too much because I really want to get to the other model, which is more interesting and richer. Okay, so if you do this optimization, this is what you find. You find that the belief that you hold in your head is the Bayesian belief raised to some power smaller than 1. Okay? So you flatten the Bayesian belief to some amount, and this amount is given by the cost. And if now you iterate this update over your entire history, what you find is that the belief you hold in your head is a product of all the likelihoods, which are a function of the observations, raised to a power, and this power gets closer and closer to 0 as you move to the past, as you move farther in the past. Okay? So let's take this Bernoulli example, where I have just to estimate one probability, and what I will find is again a beta distribution because of that structure of updating. Now in the ideal case, the ideal observer case, remember that these parameters were the total number of 1s and the total number of 0s that you saw. Whereas in our case, what will happen in this constrained optimization framework is that it will not be the total number, but the total number weighted by a fading by a prefactor. So you multiply your observation by some exponential weight that goes to 0 in the past, and your parameters of your beta distribution will be those weighted sums. Okay? So this distribution has a simple mean that you all know. Now these quantities, since they are sums over an exponentially decaying window, they will be a finite sum essentially, and they will continue to fluctuate. So if you plot this, this is the kind of thing you get. So this is the inferred probability for different values of the cost, and what you can see is the bigger the cost, the bigger the fluctuations, but also the faster you decay back to your previous estimate. Okay? And so this character is a character we will find again, that the more you constrain your precision, the bigger the fluctuations will be, the errors will be in your estimation, but these errors will also die out faster. Okay. So now to come back to Mike's question, you can do, I advertised this big thing with a vector of parameters, and I just showed you an example with one parameter. Now you can look at more general cases, and we've done that, but I'm not going to discuss it because I want to get to the rest of the talk. Instead, I want to show you an experiment with many trials. So this is an experiment that Arthur, I forgot, I should have said that was on the first slide. Some of the work I'm presenting in this lecture was done with a former student of mine, Arthur Prat-Carabin. Some of the work was done together with Mike and Yeji Song, who is at Columbia. This experiment was run by Arthur, and this is the way he did it. The subjects were seeing this, and were told that a lightning will fall on one of these two antennae randomly. And when lightning falls, if they've predicted the correct antenna, here they don't, they predict right and the lightning falls here, so they lose the electricity. But if they predicted correctly, like here, and they click on the right antenna, and the lightning falls in this right antenna, then they gather the electricity that they can collect and use later. Okay? So the point is to predict where the lightning will fall, on which antenna the lightning will fall in the next trial, and we scan various probabilities from 0.5 to 0.95. And the way the experiment is done is in successive blocks of 400 trials. So first, the subject sees, each block is associated with a given underlying probability. So first, the subject sees 200 trials passively, just seeing what happens on the screen. And then we measure the responses for 200 trials. And the subjects do 2,000 trials. Okay? And so this is what we find. So that's the true probability of the underlying process. And that's the probability with which the subject predicts the next symbol. And here what you should focus on is the difference between the blue and the yellow line. So this is the probability that subjects will predict a 1, if you want the lightning on the right antenna, if it's followed by a 1, whereas this is the probability that they will predict a 1 if it follows by a 0, so something like the hot hand. Okay? And the models that I showed you before actually give rise to a very similar behavior. And here it's looking at individual subjects, and in fact you can find different types among subjects. You can do a more detailed analysis, but I will not describe. Okay? Now, one way to plot this is just to measure the magnitude of the effect, is to just plot the difference between these two curves. When you do this, you get these red points. So this is the difference of expecting a 1 following a 1 with expecting a 1 following a 0. And you get this curve which is positive over the entire range of probabilities. You can condition and look at these biases, these differences on longer time scales, like you were asking. And this is an example where we're conditioning on 3 pass symbols. I'm going fast here because I just want to illustrate this quickly to give you a flavor, but then move on to something else. So I'm just showing you this one example. So this is the probability of seeing a 1 followed by 101 or by 001. So if you expected a strict hot hand effect, you would expect that this would be larger than that because there are more 1s here. Okay? And what you find is that, in fact, mostly this quantity is negative in the data. So maybe Ido Erev will talk about this at the end of the summer school. This is very similar to what he's observed and what he calls wavy recency, which is not kind of uniform hot hand effect. And it's not so easy to think of models that will capture this, but this simple model. Okay, but this simple model we propose indeed gives you a bunch of values for which, probabilities for which, and this is negative. So there's no quantitative agreement, but at least qualitatively we find this kind of wavy recency pattern. Okay, so these were details. If you're not interested in these details, just forget about them. Was just to illustrate the kind of structures that one can extract from these sort of data. So let me try to connect now briefly to some existing models. Yeah. So it predicts the hot hand effect at the first order, so with respect to your previous, so if you see a 1, you think you will see a 1 next. But it also predicts more subtle effects that are, for example, if you see 0, 0, 1, yeah. Okay. Essentially, because you're averaging over some finite window, but with this exponential structure. Okay, and that will give you the kind of structure that gives rise to this. So it has to do with how the weight of the observations decay in time. It's a bit more complicated, but I can tell you more after if you want. It's a bit more complicated. Yeah. So maybe in one word. So if you look at the whole family of models with different temporal dependencies, so including more parameters, what you find is what fits the best is models where people just look at probabilities of transitions. So they're updating not one probability, belief on one probability, but belief on 2 transition probabilities. And when you have that plus the fading memory, you get this kind of effect because of that structure. Okay. Yes?
So basically this parameter that captures like how wide,
I
like how wide this finite window really is, it seems to be a feature to capture the memory. So do you have some coordinate with respect to the memory?
Okay, so in this case, everything is controlled by this cost lambda. Okay, and so if you think of this as some kind of cognitive load, that will, or measure of cognitive load, that will define the size of your memory. Yes. So I should rule out the first and the last row. Yeah.
So did you think of what role the myopia plays in the results? You have lost that at the end of each of the model, but you can also assume that those people are in the myopia fashion.
Right.
So in case that the sophisticated people would converge, they can jump around the beliefs.
So in the context of this simple model, I haven't thought about a more elaborate optimization. I think it will just depend on really how you impose the cost. So if you impose the cost, if you have a bound, if you have a hard bound on the cost, I think this will hold. If you don't have a hard bound on the cost, then and you have a cumulative cost, then the result might be different. Yeah.
I was wondering, I mean, if we go back to the previous slide, if there might be some sort of pattern recognition that's happening in the mind, 1010, 0011. It seems to just make sense. So could you speak about pattern recognition?
Okay, so I think this is a very good point, and I don't know of a good theory of how to formalize this, how to think about this pattern recognition. To think about what Mike was alluding to, namely to have a cost on a complexity of a model, my initial motivation for that was the kind of thing you're talking about, to formalize this pattern recognition in terms of a kind of complexity cost. I don't think that we're doing this here. I don't think that any of the theories that we've seen until now does this. So I think this is something that is to some extent lacking. There are some proposals, but I haven't seen a very satisfactory proposal. But I agree that this is something one should think about. Okay, so there are these two papers in the economics literature that propose models that are essentially the same. Amusingly, they don't cite each other. So this one was done in the context of explaining base rate neglect. This one was done in the context of asset pricing. And so what they assume is if you have, you can write the posterior probability after a sequence of observation on some parameter mu as the prior raised to some power which is geometrically increasing with time, and exactly the same kind of fading product over likelihoods. This one is exactly the same model. The only difference is that in their case, they always remember the prior. Okay? So as we just saw in our model, I can write the belief that we hold in mind as a product of the likelihoods with this geometric power. And if I associate this parameter nu, this numerical parameter nu, with 1 over 1 plus lambda in our case, these two models asymptotically become identical. This one is different because you remember the prior. And this points to something that is not satisfactory with this cost, because this entropic cost is just saying that you pay a cost when you want your, beliefs held in mind are different from a flat belief, from a uniform belief. There's no reason why the reference should be a uniform belief. And if you take, in fact, an effective reference belief here, you find a form that is exactly like this, so you'll always remember this reference belief. Okay, so. But this was one point that was not very satisfactory with this model. Okay, now just to complete the analogy, we looked until now at binary variables, but one can look at more general distributions or continuous variables, and that's what these authors did. In fact, they looked at just at normal variables, so they assumed that this is an IID process where S is drawn from a Gaussian distribution with mean mu and variance sigma squared. And so you can rewrite this just in this exponential form. Now that this power becomes a prefactor in the argument of the exponential, and by rewriting and massaging this, completing the squares if you want, you can show that this is simply proportional to a Gaussian that has a mean which is a fading average of your observations. Okay? So it means that this posterior will track not the true mean of your process, but some moving average of your process over a finite window whose duration is controlled, in this case, by nu. Okay? Now, in neuroscience, in psychology, there has also been a model proposed by Yu and Cohen, and then it kind of extended in different ways by other authors. It's very closely related, but in its initial form was proposed differently. So these people said that sometimes you forget. That was their story. And they say that when you update your posterior, so you want the posterior at time t, a fraction of time 1 minus phi, where phi is a number, you will just do the correct Bayesian update. But a fraction of time phi, you will just resample your mean from some arbitrary prior and start again your inference. Okay? And this you can show that it gives results that are extremely close to the exponentially fading memory that I showed before. And that's obvious because this is just a Poisson process. So it's very natural that it should be very similar to this exponential memory. Now, what was the motivation here? So again, in Ariel's nomenclature, the story here was that humans adapt are adapted to a changing world. And they, even if you tell them that the world is not changing, they assume that something behind the curtain is changing. And so they assume that their knowledge will become obsolete. Okay? And so once in a while, they kind of refresh their mind, forget about the old knowledge, and start inferring again. Now, there are various criticisms I think one can address to these kinds of stories. One is that they involve a number of arbitrary parameters, and even here an arbitrary function. And even if this is a correct story, still it's incomplete because one would need to know how these change depending on the conditions of the experiment, for example. But the more serious problem I find is that this is based on an argument of adaptation. So it says that humans adapt, and they've adapted to some conditions, and this is why they forget. But if you do this experiment for very long, people don't readapt. So you have to assume that people have adapted on some long evolutionary scale, for example, and then they're stuck. And this is hard to believe in these contexts where we can see that people can learn statistics. And we've done experiments where we see that people learn even subtle differences in statistics over the time scope of an experiment. So to base an argument on the fact that we're adapted to something, but then we cannot readapt, I find strange. Okay, so just to summarize a bit, so what we said is this was our proposed Lagrangian to minimize. Now, I already said that this was problematic, so we want to compare this not to uniform distribution, but to a reference distribution. A very natural reference distribution would be an unconditional belief on Q rather than this conditional belief. And that's simply the mutual information, okay, between Q and your observations. And now already, as one of you pointed out, that choice was also arbitrary. And if I give you a specific task, maybe you don't want to minimize this distance, but you want to maximize your reward in the task or minimize your loss. And so imagine that I give you a task which is to predict the next symbol. Then you want to produce an action which is as close to the next symbol. And maybe if you have a quadratic cost, this term should be replaced by that. Okay? So if you do this, you get exactly the prescription of Sims of rational inattention. You want to minimize some tracking error subject to a cost in mutual information. So that's exactly one version of rational inattention. It's also exactly a rate distortion theory. Okay? Now, Luminita gave us very nice lectures on this kind of setup, and the whole motivation there was to say that we're sluggish, and we underreact to new information. Whereas what I've shown you until now is that in the examples I gave you is that people overreact. So how come that we have a model that was motivated the whole motivation for writing this model was to explain stickiness and sluggishness, and in fact what we want to explain here is something completely different. Okay? And so in the rest of the talk I want to resolve this and show you some predictions. And the way I will resolve it is to say that you don't only have to think about the cost with which you recruit new information, but you also have to think about the cost with which you entertain old information. Okay, and that will be the difference. So the setup is we consider an IID process. So at each period, I will draw some random variable which is centered around a constant mean mu, and to which I will add an innovation. The innovation is centered Gaussian with a known variance, and we assume that we don't know mu, but we know the prior over which it's drawn, which is again normal with a known variance omega squared. Okay? Now, what would you do if you're an ideal observer and you're asked to estimate the mean? Okay? So focus on this because this is important. I will return to this many times. So you have this IID process. Everything is Gaussian. So you know that the posterior over the mean, given a set of observation, will also be Gaussian. And how to update this Gaussian is a simple Kalman filtering problem, which Tomasz has already illustrated. And to update from time t to t plus 1, all I have to do is to update the precision or the inverse variance of this normal distribution by taking the previous precision and adding a little piece sigma to the -2, where sigma square, remember, was the variance of the innovation. Okay? And correspondingly, the mean will now be a weighted average of my previous mean and my new observation, and the weight is the precision. Okay, so that's very intuitive. Now I can massage this a little bit and write the new estimate of my mean as my previous estimate of mean plus a correction, which is a multiple of this surprise. And this, the prefactor will be expressed in terms of the precision and is often called the Kalman gain. Okay? Now you can see that if we start from no knowledge, so just prior knowledge, if I continue updating, I will add a constant term to my precision. And so my precision will grow linearly in time. So my uncertainty on my estimate will decay to 0, like 1 over t hyperbolically. And by the same token, because of this term, my Kalman gain will go to 0. So I will become completely insensitive to new observations. Okay? And my mean will just converge to the correct mean, which is the empirical estimate of my observations. Okay? So I will use this a number of times. So now, this assumes that we can use all the observations. But as I said at the beginning, if I'm at time t and I want to produce an action based on this observation and all the past observations, what I have access to is some mental summary of my past observations. Okay? Now, when I was at time 5, I only had access to this mental summary of the previous 4 observations and so on. So there's a kind of nesting of summaries of past observations and new observations. And so the framework we propose is the following one, or the structure we propose is the following one, is that when I see an observation, I will store it in memory as some memory variable. When the new observation comes, I will combine it with my memory to produce an action. And I will also create a new memory that summarizes my previous memory and my new observation. In the next step, I will combine the memory I just formed with the new observation to produce an action, and again update my memory and so on. Okay? So there's a recursive structure like this that we're assuming. Now, if I'm free to do this anyway, I can always just identify the memory with my previous observations and just keep a long vector of my previous observation as being my memory. And so what we'll assume, and this is where it differs from the kind of models that Luminita was describing, I think, is that we'll assume that there is some imperfection in this updating of the memory. Okay? And so we allow this memory to be drawn from some distribution, to be sampled from some conditional distribution, conditioned on my previous memory and my new observation to respect this recursive structure. Okay? In fact, we'll make it simpler, and we'll specify this problem, because for various reasons, but among others, it makes it much simpler, much more tractable, which is we'll assume that there's a linear relation between my new memory and my previous state, which combines my observation and my previous memory. So the new memory will be some matrix times this vector, to which I will add a random vector, which will be normal with some covariance capital sigma. Okay? Right? Is it clear? Either it's completely clear or completely unclear. Okay. So because we're assuming this linear structure, and because all our prior distributions and the distribution of the innovations is Gaussian, the full problem is jointly Gaussian. All variables are jointly Gaussian, so I will always be able to write a posterior on my mean as a Gaussian with some mean and some variance. Furthermore, as I showed before in the Kalman filtering example, this mean will be some linear combination of the observations that happened before. But this variance will be independent of the specific realization of the observations. exactly like in the Kalman filtering example that I gave before. Okay. So now, what's the what's the problem that we want to solve? We want to estimate mu. So we want to minimize the error, the squared error, on my estimation of mu, conditional on my knowledge at this time, which includes the observation I just made and my memory. And we just said that this is the sigma hat squared that I introduced in the previous slide. So it's the uncertainty in my posterior. And we want this to be, now we're not going to be myopic, we want this to be minimized over all future times. So we'll look at the loss function, which is discounted sum with discounting beta of this uncertainty. Okay? So this will be what we will want to minimize. Of course, if we do it without any constraint, this is again just the Kalman filtering problem I showed before. What we will do is we'll include an information constraint on forming my new memory. Okay? So there is some, I have to pay some cost which will be proportional or to some function g, I'll tell you in a minute what that is, but proportional to the amount of information that I extract from S and M and I record in my new updated memory. Okay? And so this will be the loss function we'll want to minimize. One can consider different functions g. I will simplify this discussion by considering a simple example which says that g is 0 if the mutual information is below some bound and infinite if it's above this bound. And so I can rewrite this problem as minimizing this discounted uncertainty, some discounted uncertainty, such that at each step of my update, I don't exceed some limit on how much information I can remember about the past and my current observation. Okay? Okay, so this problem, I posed it as estimating the mean, but in fact it's more general, but let me skip that for now. So I was hesitating whether I should show you a sketch of the derivation, and unfortunately for you, I decided I will show it. Now, for those of you who are not interested, just sleep for 4 slides. For those of you who are interested, brace yourselves. So, yes?
Can I just ask a
Yes.
question about the setup on the previous
Yes.
slide? So there are, in effect, 2 departures from full rationality here. There's the memory formation process, which adds some noise, and then there's this constraint on how much that you can remember.
Well, in principle, they're the same, right? Because if I allowed this general rule, I could make this a delta function, and this would be a perfect updating of my memory. But with that cost, that will cost me a lot of information, so I will not be able to do this. Okay? So the cost is specifying the form of the noise. Right? What we did assume is this linear relation. So that's a special assumption. But aside from this specific structure, all we assume is that there is some noise, and the cost will control that noise. So it's not 2 separate assumptions.
The structure doesn't prevent you from being fully rational, because the Kalman filter has this.
Yeah. So you could you have this vector could increase in size at each step, okay? And m at each step could be just the vector that records all past observations. You could have 0 noise, and so you would have perfect record of the memory.
No, I understand that, but in fact, I assume that you do have both noise here and a limitation on memory. So you
It's
are
only
making
the limitation that
Yeah.
requires the noise to be there. So it's not 2 separate constraints.
Yeah. So okay.
In the absence of the second one, this is no constraint.
Right. So that's what I was saying at the beginning. So if this were a delta function, so every time this would be a vector that contains this vector and that vector, I would have no noise. But if I have that cost, that would penalize that solution. Okay. So I'm assuming this update, which is completely general. Now the question is, what will it be? Okay, if I solve the problem. And in the absence of the mutual information constraint, the solution would be the optimal solution, where I just record all my past observation. The constraint will enforce another solution.
Why do you say that in the optimal case the effector could just be just one number which is equal to your posterior?
Depending on in this case, yes. So depending on the problem you want to solve, I'd say more in that most general case is allowed by this structure.
Right, okay. But in
Yeah.
this case, it would
Yeah,
be sufficient
yeah,
just to
yeah.
have one number.
What's the nature of the constraint?
Okay, so the nature of the so we allow so the new memory is sampled from some distribution, some conditional distribution. Okay, the question is, what is this distribution? I don't want to specify it ad hoc. So all I will say is that I leave this free. In this case, I assume this linear structure, I assume some Gaussian structure, but aside from that, I leave it free, which in this special case means I leave this matrix free, I leave the size of the vector free, I leave the covariance of this noise free, okay? And then I will say, how will I find out what it actually is? And the way I will find out is to write this problem, this optimization problem, and I will optimize this, minimize this quantity subject to this constraint over the possible distributions.
What is I again?
The mutual information between these two random variables. One is the memory at time t plus 1, and one is a vector that contains the observation at time t and the memory at time t. Okay? So this optimization is done over the class of possible update rules, noisy update rules. Okay?
In this recursive structure,
Yeah.
our memory is dynamic consistent.
Sorry,
Our memory are dynamic consistent.
I didn't hear.
So is dynamic inconsistency an issue here? So do you update memories like every single period? Let's
Yes.
say I don't update memories for 2 periods.
That could be, you could have that model that in some period you just refuse to take the observation. But that's, I mean, this is possible. This is included in our model. This is a special case of our model. The solution we'll find does not involve such phenomena. Okay, how much time I have?
12 minutes.
I'm very upset because I wanted to show you this derivation, which I will not be able to show that and the rest in 12 minutes. Very upset because
But you solve the problem with
with constraints,
constraints.
yes. So this derivation is very nice because you just apply Kalman filtering a few times and you get the answer. So anyways, so let me then skip this derivation, which was very nice. So that's the solution that you find. What you find is an update rule for the estimate of your memory, of your mu, okay? And the update rule has it's a AR1 process, so the mu at time t plus 1 will depend on the mu at time t, will depend on the new observation, and will have also some noise, okay? Now, this was done without imposing a constraint, so this is still general. Now, what will okay, and I should say every parameter here only depends on a sequence of prefactors lambda. Okay, so at each time I have some lambda of t, and all the other parameters like this gamma will depend on, and this noise, the covariance of the noise will depend on this lambda. And the choice of this lambda will be given by the constraint on the mutual information. Okay, so one can rewrite the mutual information in terms simply of this lambda. And this parameter lambda going to 1 means that the mutual information goes to infinity. So that's the unconstrained case where you can have as precise information as you want. If this lambda goes to 0, this mutual information goes to 0, so you're not remembering anything. Okay? Yes.
Ignorant question. What is exactly the mutual information?
So it's
What
yeah.
is mutual?
So it's a measure of it's a measure.
Embarrassed by the
It's a measure of correlation between random variables, which satisfies some properties. Okay, so it's the Kullback-Leibler divergence between the joint distribution and the product of the two marginals. That's one way to see it. Another way to see it is that it's the entropy of one of the variables minus the entropy of this variable conditional on the other variable. Okay, so there are various ways to think about it. Another way to think about it is, which is maybe the best, is it's the logarithm. So if you have a variable x and a variable y, if I give you y, the mutual information is the logarithm of the number of states of x you can distinguish from the knowledge of y. Okay? Okay, so what happens here? What we have is that initially, as in the rational problem, the uncertainty and the Kalman gain will decrease. But asymptotically, the solution will be different if I have a constraint or I don't have a constraint. So if I have perfect memory, so I'm completely unconstrained, I'll get the same solution as I had before. My uncertainty goes to 0. My Kalman gain also goes to 0. I become insensitive to new observations. Okay? If I have a noisy memory now, the situation is different. And in fact, this uncertainty will converge to a number that will depend on my constraint. And this is not important, this number, but you can expand this number for small constraints, for small lambda. And what you find is some ratio like this with a correction that depends on lambda. And this is just the estimate you'd have based on one observation. Okay? So this is the Kalman result, if you want, for one observation. And so this is the estimate for no memory, and you get a correction when you allow some memory. Okay? So this is the picture that you have as a function of time. My uncertainty will decrease. It'll decrease faster if my constraint is tighter, and it will also asymptote to a larger number if my constraint is tighter. Okay? Now, how does the estimate evolve in time? That was the solution that we got. And the first thing that you can see is that this Kalman filter, unlike in the optimal case, doesn't go to 0 asymptotically. So even after infinitely many time, I'm sensitive to new observations. Okay? And this is when I know that the mean is fixed. Okay? So, but this is the optimal solution that I get given this noisy memory. So there's no trick. So this is an example of overreaction, because even after having seen infinitely many observations, I'm still reacting to new observation. Okay? Another property of this solution is that I have some persistence. So my new estimate will depend on a previous estimate. So if I make a mistake in this estimate because of this sensitivity to new observation, this mistake will survive for a while, okay, in my new estimate. And in fact, you can see that the dependence on the Kalman gain of the two terms is opposite, which is also what I showed you before with my example of fluctuating estimates. So if I have a larger overreaction, so a bigger Kalman gain, I will have less persistence. So I have bigger overreaction, but I forget it faster. Okay? So this is what is illustrated here. So this is the impulse response in the estimate of the mu to a unit innovation at time 0. So the optimal solution will give you nothing, because you're not sensitive anymore to new observations. And as you increase your constraint, then you'll have bigger and bigger responses to new observation, but you also forget them faster. Okay? So now the question is, okay, so maybe another character of this solution is that this, sorry, I should say, so you can take this, now iterate this, and just write a solution for mu in terms of these parameters. In terms of the observation, this is what you get. So it's very similar to the kind of solutions we had before. So mu is not the empirical average of Si, but it's an average of Si over some window that decreases geometrically with this power here. And this term controls the time scale of that window. Okay, so this, I will have a stronger prefactor for dates that are closer in the past. So this gives me some recency effect. Furthermore, this also gives me fluctuations in my belief, even asymptotically. Okay. And finally, the main difference with the simple model that we have before is this term, which brings in some noise, which will make different subjects different, and will make a given subject different also on responding in several repeats of the same sequence. Okay. Now, I want to emphasize that this noise is not something that is added on. Okay, coming back to your question. This noise is what is causing the recency bias, the overreaction, and so on. It's the optimal solution in the face of this noise that gives rise to this structure. Okay, so it's this noise that is the cause of the biases that we see. And so they're quantitatively related.
Another source of heterogeneity is that the constraint can be
different. That's right.
So
that's right. That's right.
You have two.
That's right.
Sources. How do you distinguish?
Well, so if you assume that the constraint is fixed in time, one will be heterogeneity that is fixed in time. The other one will change over time, and so presumably there's a way to analyze and distinguish them. Okay, so I wanted to show you applications of this to forecasting, and it was very beautiful. You don't know what you're missing. It's terrible. So all this is gone, and I wanted to show you a bottleneck approach to the same type of problem, which I will also skip. But you will see some of this in Noga's talk later in the summer school. I wanted to kind of give you a preview, short introduction to the bottleneck problem, which is another normative way to approach the same type of problems with nice solutions. So I will skip this too. But let me just maybe conclude by giving you a bird's eye view of these different approaches, and I'll continue in the next lecture. So what we discussed mostly was a theory with this structure where the Lagrangian I want to minimize has two terms. One term corresponds to some performance, maximizing some performance or minimizing some loss. And the other term corresponds to a price that I have to pay on the precision of my internal representation on which my action will depend. Okay? And this is, we call rate distortion, rational inattention. Okay? The other approach, which you haven't seen because I just skipped it, replaces this term, this loss, by this term. So instead of having, for example, a quadratic loss, you have a loss which is expressed in bits of information. And one way to interpret this is equivalent to saying that you want to minimize a surprise. Okay? So if you have a sequence of observations and you have an internal summary of these observations, which I call R here, then you want to minimize a surprise on the new observation conditional on your internal variable R, then the loss function will be this mutual information. And the price you have to pay is again the mutual information between R and S. Now I put the parameter differently, it's not the best way to write it, but the point is that this term doesn't change. This term, instead of being an error, becomes a prediction surprise. Okay? And so the big difference is that this will depend on the magnitudes of probabilities in a different way than this. Okay, so that's the difference. And then many people have asked me what's the difference with efficient coding. I will discuss this more in the second lecture. But efficient coding kind of swaps things. And there what I will want to maximize is this mutual information. So I will want to have an internal variable that can recruit as much information as possible from my observations, but I will impose some bound, some constraint on my internal variable, some kind of repertoire constraint. So I'll come back to this in the second lecture. Okay, so let me just summarize and end. So what we assumed was some costly precision of mental representations, and from this principle, so from a normative principle based on this assumption, we retrieved some a list of phenomena. So asymptotic fluctuations of belief, recency bias, overreaction, persistence, and idiosyncratic noise. There still is the question of how to combine the lectures of Luminita and the lecture I just gave, namely, what about noise that induces sluggishness? And what I would like to point out is that in the model that I showed you, I only imposed noise on the memory update. I didn't impose noise on the observation, how it store internally the observation at time t itself. And Yeji Sung has generalized the model to include that kind of noise. So now you have two noises and you have two precision costs in your model, and then you can get a behavior that displays both sluggishness and overreaction in a way that agrees with some observation. In particular, you can have underreaction initially and overreaction later on. Yeah.
I have a quick comment about this. So I think it's possible to reconcile them if you're thinking that this is a model where you're learning about a fixed mu, and it might actually, overreaction might actually be a really good way for people to deal with changing. Because when mu is changing, you have underreaction, so the overreaction coming from this first piece is helping you adapt to an environment where your structure is changing.
But you're saying that would be if the environment is changing, but you think the environment is static.
No. I think my lecture is one in which mu is changing.
Right, but I'm saying if mu is changing, you could follow this program, but the solution would be different. Right? Because this is assuming that you know that mu is fixed. So I could have treated the problem you're mentioning, and I would get to another solution. Now, what you could say is maybe people think that mu is changing but don't know that it's changing fast enough, in which case they assume that mu changes slowly. In reality, mu changes fast, and so overreaction may help. But you would have to assume that they're wrong about something. Now, I think so. But one comment maybe that I should make, which relates to what you're saying, is that this solution that I've shown is very similar to the optimal solution when mu is changing. Okay? So if mu is changing, it's diffusing, and you're doing an optimal estimate of the mu, you would find a solution that has a similar character. It has some quantitative differences, so the way the gain and the time scales are related are not the same. But the main difference would be that all the randomness in that case would come from the randomness in the observations, whereas here there is this extra idiosyncratic noise, okay, that is causing these fluctuations. Okay. And again, I want to emphasize, but this is a good that we had this chat, to emphasize that this is not a result of a maladaptive process, what I described. It's really you're optimally adapted under some constraints. Okay, so I've gone over time, so let me leave you with these questions, and thank you very much.